In this video, we'll look at centripetal forces and accelerations. Anytime you have something going around in a circle, it's very important to realize that there's a force pulling that object into its circular shape path. The word centripetal means a centrally directed force. Well, no, it means centrally directed. So a centripetal force is just a force that points towards the center of the circle. It's not a new kind of force. It's just one that's pointed in that direction. So let's take an example where we have a mass here that's on a string and it's going around at constant speed like this. The string is what's pulling the mass inward constantly. That's a centripetal force, the tension in the string. And so tension is what makes this go in a circle. Okay. If I broke the circle, where would the object go? Well, it would fly off with a constant velocity in a direction tangential to the circle. So wherever it was at the time that the string broke, it would go straight. So it's very important to remember that even if we have constant speed, which in this case we say that we do, that there is acceleration. So let's take a look at that more closely. First of all, uniform circular motion is defined as circular motion at constant speed. Now, that seems like if we're at constant speed, we're not accelerating. But remember that a velocity vector has both a speed, which in this case is a constant value, as well as a direction. What is changing here is that over time, the object moves around like this, and the vector, the speed, is the same size, but the direction is different. So we actually have changed velocity, therefore we must have accelerated. Remember that acceleration is the change in velocity over the change in time. So in this situation, we're accelerating because of our tension in the string pulling towards the center of the circle. We're accelerating this mass around the circle, pulling it into circular motion. If this was a situation where we had the Earth and the Moon, the Earth would be at the center here, the Moon would be at the outside. The force here is, of course, gravity. There's not a new force, there's not a new force called centripetal force, but gravity is pointing centripetally. So in every case where there's circular motion, we want to identify the force that's acting on the object and keeping it in a circle. Now it turns out that if we look at this, centripetal acceleration is equal to the velocity squared over the radius. Okay, which means that if I go faster, there's more acceleration. Let's think about why that would be. Let's say I'm going at a constant speed of 1 meter per second and I have a rope that's pulling inward. Okay. You would feel a force on your hand as that rope pulls on the mass, and the mass would be pulled inward as well. Think though, what would happen if that mass was going 10 times faster? Well, then the force would be much, much higher. Turns out it would be 100 times higher. But that might not be obvious. Also, what happens if I doubled the radius? At, let's say, 1 meter per second squared, I doubled the radius. Well, the force in the rope would be less. So it's important to realize that the acceleration here is proportional to the velocity squared and inversely proportional to the radius. Now, what connects this acceleration and the force? Well, Newton's second law. So the centripetal force equals the mass times the centripetal acceleration. So in this case, tension is the centripetal force. That equals my mass times v squared over r. Turns out there's another way to look at this velocity, which is around the tangent of the circle. We could also look at it as r times the angular velocity squared as well. So this could also be written that this would be mr omega squared. Angular velocity is in radians per second. Now again, it's important to note that the right side of this equation is the result of the force on the left side. So I've always got a mass, that's the object that's being moved in the circle, and if it's staying in the circle, I'll have centripetally directed acceleration. The left side of this is the force that causes that. What is the force that's pulling that mass inward? In this case, it was tension. In the case of the Earth and the Moon, it's gravity. In the case of you driving your car in a circle, it's the friction between the tires of the car and the ground. So it's very important to identify the source of the centripetally directed force and put that on the left side of these equations, and then don't put any forces on the right. The right side of the equation is reserved for the resultant motion. Hopefully that's clear.